All right, sorry I can't be with you today, but hopefully this here gives you some opportunities to do some problems and learn this stuff a little bit better. So for these first two, it says evaluate these definite integrals by constructing geometric figures. So go ahead and pause right there and try constructing the geometric figures. And if you need some help, you can kind of look ahead and see what's going on. I'll give you a moment to pause and try those. All right, so when we say geometric figures, we're saying what does this look like? Up here at this line 10 is just a line at 10, and we're going from -2 to +6. So we've created a rectangle. That's what that integral represents. The base of the rectangle is 8, the height is 10, 8 times 10 is 80. And then here we have a line 3x, goes like that, and we're going from -4. So we'll have this triangle here with a negative area, and then all the way to 5, which will have a triangle with this positive area. Now, there's a couple ways you could do it, but I think the simplest is just find this triangle, and subtract those two, right? So for this one, this base is 4. This height down here is 12 because it's 3 times whatever x value you're at. If you did 12 times 4 divided by 2, this area is 24, and because it's below, it would be a negative, okay? And for this one, it's 5 and 15 on there. So if we do 5 times 15 divided by 2, I believe we get 37.5 for that, okay? And if I were to take 37.5 minus 24, we'll get 12.5, and that's our area, the total, the net area there, okay? So that gives us, again, using geometry. Now, there'll be some other ways that we can do this in just a bit that might be more helpful, but this would be how we could do it, doing that. All right, then we get one like this. It says processing plant starts the workday with 250,000 cans of green beans. Throughout the day, the plant cans green beans at a rate of this. So this is the rate that they're adding, and it's based on thousands of cans per hour, okay? And then starting at 3 in 3 hours, so they do that for 3 hours, and then at the 3-hour mark, they start to ship the green beans. So then they take away at a rate of this, thousands per hour, all right? So then the first question here says, how many cans do they have at the end of 10-hour workday? So I'm gonna let you go ahead and plug this in and see if you can write the integral. You can use C of t and S of t when you're writing the integral, and then put it into the calculator, see if you get your answer. I'll give you a moment for that. Okay, so as far as how many cans do we have to start with what we had to begin with, which was 250. Now we'll just keep it in here and understand that these are thousands, so we should multiply by 1,000 at the end to really get our answer. But we'll go 250 plus the number of cans that we added. That was started at time 0 all the way to time 10, and we were doing it at a rate of C of t. Okay, so this will be how many we added minus how many we shipped away, and we didn't start shipping until time 3. And we shipped all the way to the end of the time 10, and we shipped at a rate of S of t, okay? So this is the integral that would represent how many we would have. Now I have those stored here into y1 and y2. So on my calculator here, we're gonna go 250 plus math 9 from 0 to 10, and that was the y1 equation, minus math 9 from 3 to 10, and this was the y2 equation. Hit enter, and we get 278.761, but again, these are in terms of thousands, so if I multiply by 1,000, then we get this right here, 278,761 cans. We'll round to the nearest can there. And then if you did 278.761 thousand cans, that's okay too. They would accept that. At what rate is the volume of the cans changing at t equal 8? Well, there's a rate that we're making them, and that's C of 8, all right? C of 8 is how fast we're canning them at t equal 8, right? And then there's a rate that we're shipping them, and that's S of 8, okay? That's how fast we're getting rid of them at the 8 mark. If we were to subtract those two, that would be how fast the volume is changing, whether up or down, all right? So on my calculator, I can just go alpha trace Y1 at 8, that's how fast we're making them, minus alpha trace Y2 at 8, and that's how fast we're getting rid of them. And they're changing at 1.992 thousand cans per hour. So in other words, we're adding about 1,992 cans per hour at that time. That's how fast the volume is changing, okay? And then that's how we would interpret that. So this is a very popular kind of AP problem. Hopefully that felt pretty comfortable for you in what you were doing, okay? As far as that worksheet from yesterday and doing stuff like this area stuff, again, when you're doing it, you just want to be careful to see where you're going. As long as you're going from left to right, it can be kind of a normal thing. So for like this first one, we're going from 0 to 3. So it's just this quarter circle, has a radius of 3. So if we do pi r squared, that'd be 9 pi, but I just want a quarter of it. So it'd be 9 pi divided by 4, okay? Or however you want to do that. If I go from -12 to -9, it would just be this triangle here that is a height of 3, a base of 3. 3 times 3 divided by 2 is 9/2. Right? And if I go from 3 to 9, it would be this triangle right here. That's a base of 6, a height of 2. 2 times 6 divided by 2 would be 6. Right? So some of these, again, can be pretty straightforward. For here, I'm going from 3 back to 0. So it's the same area we just did, except because we're going in the right to left direction, we're going to take the opposite of that. It would be -9 pi. If we go from -12 to -8, that's this triangle plus this little sliver right here. And if we wanted to, we could let this part cancel this part. Those are the same, just one's positive, one's negative. Let them kind of cancel away. And now we just have this triangle, which is 2 times 3 divided by 2, or 3 for that. Okay? And if we go from -3 to 3, from -3 to 3 is this semicircle. So again, 9 pi would be the whole circle. We're cutting that in half, so we get 9 pi over 2 initially. But then there's a 4 in front of this, so we're going to go 4 times that, which will give us 18 pi for our answer there. For this one here, we're going from 6 to 12. From 6 right here, all the way to 12 right there. And you can see that it's this triangle and this triangle. They're the same area. One's positive, one's negative. So they're going to cancel out and give us 0 there. -5 to 0 is 2 separate areas that don't really cancel out. We have this quarter circle, which we've already said is 9 pi over 4. We're going to add that to this area here, which is a triangle, 3 times 2 divided by 2, which is 3, but it's below the x-axis, so it'll be a -3. Okay? And then here we're going from 5 back to -9, from 5 all the way back to -9 for this. All right, so that's a lot of area to cover here. We've got this triangle, this semicircle, and this entire trapezoid here. So let's start with the triangle. It's 2 times 1 divided by 2, which would give us an area of 1 for that, okay? Plus this semicircle, which is 9 pi over 2, and then minus this trapezoid, which is 1, 2, 3, 4, 5, 6, 7, 8. It's 6 plus 3, which is 9, times 3, 27, divided by 2. So I did base 1, base 2, added them together, times the distance between them, divided by 2. Now, that would be if we were going from -9 all the way to 5, but we're going the other way. And so that means that actually this is going to be the opposite. So you can actually just put a negative like that in front of all of it, or actually carry it out if you're of that mindset. And you could even combine the -1 there, make that a 25 halves if you wanted. You can do some other thing, but either one of those is actually correct. Okay. Here I've got from -9 to -3, that's the trapezoid. We just found that area to be 27 halves. And we're going from -9 to -3, which is the normal way, and because it's below the x-axis, we're gonna make that negative. If I go from -12 to -3, then I'm basically just adding this triangle on. So it's 3 times 3 divided by 2, that's 9 halves, minus the 27 halves, which gives us a -18 halves, or a -9 for an answer there. And then here we're going from 3 to 12, so that's this triangle, which is 6 times 2 divided by 2, so that's 6, minus 3 times 2 divided by 2, 3, and we're going to multiply that by 5. So we'll end up with 15 for an answer there. All right, so again, these aren't too bad. The little geometry shapes that we're going to use are pretty easy to work with and stuff, and hopefully not too bad. All right, here it says Jim decides to go for a 45-minute run, and the graph of my velocity is shown here. And we're asked to find some things here. So I'm going to give you a moment to try this out, and then we'll go through them together. All right, so it says, how far did Jim travel in 8 minutes? So these are in terms of blocks per minute. So if I were to go to 8 minutes and find this area, it's 8 times 4 divided by 2, which is 16. And since it's blocks per minute, that would be blocks. So you went 16 blocks, whatever that length is, depending on the city. Might be short, might be long. Probably pretty short if you did 16 of them in 8 minutes. Okay. Find J prime of 5. That's the slope of this line here. We went up 4 and over 8, so it'd be 1/2. This is already in terms of blocks per minute, so that derivative would be blocks per minute, or blocks per minute squared. It says, describe his actions from 8 to 12. Well, from 8 to 12, we're traveling at a constant velocity of 4. So he's running at a constant velocity of 4 blocks per minute. And that's really moving. Block every 15 seconds, he's really going, okay? What is Jim's position at 14? So again, we're gonna find the area here. It's 14 plus 4, that's 18, times 4 divided by 2 would give us 36. He's 36 blocks to the right, or to the positive of his starting place, okay? So he's gone 36 blocks to the positive, whatever that is, east, right, north, I don't know, whatever that would be. He's 36 blocks away from home, okay? And how many blocks did Jim run during the first 25 minutes? Well, now if we add this on, this is 11 times 5 divided by 2, that's 27.5 more blocks. It's 27.5 blocks coming backwards, right? But it's still blocks traveled. So he went 36 blocks positive, came back 27.5 blocks back towards home. So altogether, he's gone 63.5 blocks. Okay. So this is one where we wouldn't let the negative cancel out the positive. It doesn't make sense. We're talking about total distance traveled. That's what he would have. Okay. So we have a similar problem here. I'll let you read this one and give this one a try. All right, and it says Dave runs with this velocity. Find his velocity at 6 seconds and use units of measure. Well, at 6 seconds, he's right here with a velocity of 10. It's just 10, and his thing is in meters per second, so 10 meters per second, okay? Find his acceleration at 2 seconds. Well, the acceleration would be the derivative of this. It's up 10 over 3, so it's 10 thirds meter per second squared. All right, so now it says, who ran further, Dave or his friend Maddie? So we want to find the area of this. This is 10 plus 7, so 17 times 10 divided by 2, which would give us, I believe, 80 meters. Let me try that again, though, just to make sure. We have 10 plus 7, 17 times 10 divided by 2 is 170. No, we had 85. Tried to cheat Dave there. All right. So Dave traveled 85 meters. And that's just by finding the area under that. All right, for Maddie, we're going to have to do an integral from 0 to 10 of her velocity, m of t. Okay? All right, so if I go on my calculator and go math 9 from 0 to 10, and put her thing in, 24t divided by parentheses 2t plus 3. It says that she traveled 83.33. All right. And so who traveled further? It sure looks like Dave did. Not by much, but that's what we get there. All right. All right. This question here says if f prime equals 3x plus 6 square root of x minus 2 and f of 4 equals 40, then what does f of 1 equal? Now, there's a couple different ways we can go about doing this. You could try to integrate this back to f of x, and then put in a plus c and find out what c is using this, and then use that equation to find f of 1. But I'm going to tell you that that's the harder, that's the more steps than needed to here. So I'm going to give you a chance to try it, see if you can see another way, and then if not, I'm going to show you here in just a second. Okay, so here's what we're going to do. We're going to say that f of 1 is equal to an initial position, so some initial place that we were at. So that's going to be f of 4. All right, and I'll fill that in with 40 in a second. All right, plus a change in position. So where did I start and how did I change? Now, the change in position is from this time, 4, to the time that I want to be at, which is 1. And what I would do normally here would be like a velocity, right? Well, in this case, it's going to be our derivative. Okay? So like if you're thinking position function, my future position is a former position plus the change in that position. Well, it works the same way going backwards. We don't have to even mess around with this or anything. We can use the exact same kind of format here to do that. So f of 1 is going to equal 40 plus the integral from 4 to 1 of 3x plus 6 square root of x minus 2. All right? And then we can do that right on the calculator and see what we get. So 40 plus math 9 from 4 to 1, 3x plus 6 square root of x minus 2 dx. And we'll get negative 4.5. And that would be our answer. Okay, you don't have to go find another equation. You don't have to do anything like that. We can just go ahead and work that out. Okay. All right. Here's a situation. I'll let you read it, pause it, give it a try. We'll go through these three here in just a second. All right, so you've had a little chance to give this a try. I'm punching this into the calculator into Y1. And A says, according to the function, is the subject's blood pressure increasing or decreasing for this time interval 0 to 10? okay? So this one's a little tricky because B of t is the rate that the blood pressure is changing. It's not the actual blood pressure, but the rate, right? So if I were to go from 0 to 10 and graph this, you can see that this is initially positive, and then it hugs, and it's still positive. It's just really, really close to 0 down here, okay? Now, because the rate is positive, so we're gonna write that, the rate is positive, because of that, the blood pressure is increasing. Okay. Now, the rate itself is decreasing, but that is not the question. The question is the blood pressure going up or not? And blood pressure is going up because the rate is positive. Now, what's happening to B of t as time goes to infinity? Well, we can see that it's heading toward, if you hit trace, you can see that we're virtually 0 right here, and the further you go out, the closer and closer you're getting to 0. It's hugging that x-axis and will forever and ever. This limit is 0, okay? And that kind of makes sense because if you rewrote this as 4.3 over e to the 0.8 t squared, the bigger t gets, the bigger the bottom gets, and the smaller these values get. Okay, so that kind of makes sense then. This says if the subject had a blood pressure of 110 at 0, what do they have at 10? Well, we would take that initial blood pressure plus the change in the blood pressure, which would be the integral of B of t from 0 to 10. And I've already got that set up on the front side, and we get 114.261. All right, and that would be beats per minute. So again, a little situation here, a little kind of real life situation that we can break down using these integrals. We can kind of predict and see what's going on in the future there, okay? Kind of nice. All right, here's, again, to help us kind of understand the difference between position and total distance travel and stuff like that. Here's a situation that says Emily starts at a position of 5. After 4 seconds, she's at a position of -7. At 7 seconds, she's at a position of 11, and at 10 seconds, she's at a position of 9. What was her average velocity from 0 to 10, and what would these two equal? All right, pause and see if you can answer those two things. Okay, so an average velocity would be a change in position, so change in position over change in time. All right, her position went from 5 up to 9, so her change in position was a +4, and she did that in 10 seconds. So her average velocity was 4/10 or 2/5 or 0.4. Okay, so how did her position change? She went from 5 to 9, and she did that in the course of 10 seconds. Okay, so what would these following equal? This here is displacement. All right, this is change in position. And so this first one would equal 4. Her position went from 5 to 9, okay? But this one with the absolute value, this is total distance traveled, okay? Now this is gonna take into account all the positives and negatives and add them all together as just actual values. So when we went from 5 to -7, that was a change of 12. When we went from -7 to 11, that was a change of 18. And then when we go from 11 to 9, that was a change of 2. Again, I don't care if it's positive or negative. I just want to add all of that together, and that would give us 32 for that. Okay? All right, so we'll do something similar here. Read that one and see if you can answer these 3 questions. I'll give you a moment. Okay, so this is our velocity. It says if our position at 2 seconds was 10, what's the position at 8? The position at 8 would be our initial position, which was 10, plus the change in that position from that time to the time that we're looking for of our velocity, okay? So on my calculator, I already have velocity put into y1 there. So I can just go 10 plus math 9 from 2 to 8, alpha trace y1 dx. All right, and that position now is 28. Again, this is not the only way, it's just the easiest way to do that. You can bring this back to a position function, find your C value, plug 8 in, like that certainly works, but this is a lot faster, and I want you to start getting comfortable with this here, okay? How far does the particle travel from 0 to 6? So we're going to integrate from 0 to 6 the absolute value of our velocity, okay? So on the calculator, I'm going to go math 9 from 0 to 6, and I'm going to go math absolute value of y1 dx, and that's going to give us a total distance traveled eventually of something, all right? So 15 1/3, it looks like. 333. Okay. I don't want to put the 10 in. That's a position. That isn't a, you didn't travel that in this time. You were there already. So we don't want to put that in for that total distance traveled. Okay. Is the particle speeding up or slowing down at 2 seconds? Well, let's find the velocity at 2 seconds. So if we were to put 2 in, we get 4 minus 12. Negative 8 plus 5 is a negative 3. Okay, but that's not the story. We got to now take the acceleration, which is 2t minus 6, and put t into that. And if you do that, you get negative 2. All right, so signs agree, so therefore we're speeding up. All right, so hopefully that helps you understand some stuff. This is part 1, and then you can watch part 2 as well.